Welcome, everybody. Welcome to the August Innovation Connect of 2021. I can't believe that it's August already. Many of you were here last month. We had the 711th Human Performance Wing on, and we had the Chief Data Office Vault Data Platform team presenting. They were great presentations. If you missed it, both of those are up on our Department of the Air Force Chief Data Office YouTube page, so you can always go check out the link there and look at any of the past Innovation Connects. There's a lot of great information there. My name is Callie King. I work with the Department of the Air Force Chief Data Office. I'll be the moderator today. We have some really exceptional presenters today. I'm very excited. Since this is about to be the busy part of hurricane season, we're going to hear some interesting information on storm modeling. So today we have from the Army Engineer Research and Development Department, Dr. Chris Massey, and from the Navy Research Lab, we have Dr. James Doyle. They're going to be doing presentations on comprehensive modeling systems used to simulate storms and assess risk. I wanted to do a couple of housekeeping items before we get started. If you could, make sure that if you're not a presenter, make sure your cameras are off and that your phones are muted. We'd really appreciate it. Don't place the meeting on hold if you can. And we'll be doing Q&A after both presentations. So both presentations will happen, they'll speak, and then at the end, we'll read the questions out loud and the presenters can take them together. Or separately, depending on if you had one for a specific presenter, please note that in your comments. We ask you to submit all your questions in the chat feature, and you can do that throughout either presentation. Any questions you have, though, please don't promote your company or ask anything media related. This is just a professional event. And if anybody else is interested that you know and they have a .mil or a .gov, you're welcome to send it to them. And then we'll have a survey that goes out after this presentation also. We have some social media where we promote all the upcoming events, so LinkedIn, Twitter, and YouTube. Okay, and so now it is my pleasure to introduce our first presenter. Dr. Chris Massey received his PhD in mathematics from Virginia Tech in 2002. Emphasizing finite element methods and a posteriori error estimates. He's an internationally recognized expert in developing and applying coastal and riverine numerical models, model coupling and system integration, storm surge modeling, and unstructured finite element meshing procedures. Dr. Massey is the team lead of the Coastal Storm Modeling Team and has led or co-led several high-profile modeling efforts of significant regional coastal storm surge. And wave hazard studies that are important for not only the Army Corps of Engineers, smart planning, but are used for other federal agencies as well as state and local communities. Dr. Massey is also a member of the Multi-Agency Coastal Coupling Community of Practice Advisory Group and the Department of Defense's High Performance Computing Modernization Program's User Advocacy Group. We are very excited to have you here today. So the floor is yours, Dr. Massey.
Thank you, Callie. I appreciate that. Thank you for inviting me to present today. I'm looking forward to it, and I look forward to questions at the end of the presentation. Give you a sec to get going. There we go. So today I want to talk about the way the Army Corps of Engineers approaches coastal storm modeling and the hazard systems, particularly in light of the fact that we are entering the really busy time of hurricane season with Tropical Storm Fred out there right now. It's fairly relevant. So next slide, please. So this is the basic outline of the talk today. I want to talk a little bit about what the Army Corps is and what we do in terms of flood risk reductions. The Coastal Storm Modeling System, CStorm is what we call that, and how it's applied on these large regional scale studies and production capabilities and data serving from all the model data that is produced and statistics that are computed afterwards. And then talk a little bit about how we respond to rapid response requests, quote unquote forecasting from our district offices when a hurricane is impending impact on a particular area. And then in with just some of the current R&D directions that we're looking into to further extend our capabilities and accuracies of the models, particularly in the compound flooding arena as we move forward. Next slide, please. So I work for the U.S. Army Corps of Engineers as part of the Engineer Research and Development Center, which is located in Vicksburg, Mississippi, made up of several labs, and in particular, I work for the Coastal and Hydraulics Lab. And CHL has three main focus areas for our work. Big one being navigation, keeping all the navigable waterways in the United States open and functioning. Flood and coastal storm damage reduction, R&D, so and operations of structures, and then military hydrology as well. So these avenues across each other cross-correlate from time to time, and we do both numerical modeling and physical modeling. Our history actually started in the physical modeling arena many years ago with the Mississippi River Model Basin in particular. And so we use these to answer operational questions as well as designing of structures for flood risk, looking at sedimentation rates and channels, trying to figure out how often they need to be dredged and cycles for those. And if you build new structures, is that going to impact the sedimentation rates in areas as we go through with those? So those are some of the basic avenues that we're looking at, particularly for storm surge and storm damage reductions. We're not really in the business that NOAA is in terms of forecasting. We do have to do some predictive capabilities to support our district operations so that they know when to close floodgates, for example, of an impending storm, or with their pre-positioning materials where to potentially expect flooding from an event. Next slide, please. So some examples of flood protection measures, if you're not aware of some of these are both hardened structures as well as engineering with nature type features, natural nature-based features, and those could be wetlands being restored, they can be dunes being renourished or replenished or created, barrier islands the same way being nourished or recreated, as well as hardened structures where you're looking at navigation gates that can be closed during flood events, as well as flood walls and revetments in front of those, breakwaters, levees. All of these are types of flood protection measures that are used on the coast as well as in the riverine area. So don't always think gray concrete structures. Also think about some of our green structures as we're looking at these as well. Next slide, please. So as I was saying, we're primarily concerned with the design and operation of structures. And a lot of what we look at in the Army Corps is building a new structure. And what I'm going to show here in these next few slides is a proposed coastal flood protection measure to protect the island of Galveston in Houston, in the Houston Bay area. And they look at several different possible flood protection measures. Some of the ones that we're just showing up there in different locations, and they want to quantify the benefits and the consequences of building this structure in terms of storm risk reductions for these. And so when we're looking at building structures, the Army Corps of Engineers doesn't build them unless there's a cost benefit ratio greater than 1, usually much greater than 1. With these, and structures are not necessarily built to withstand the worst possible hurricane storm surge ever. It is cast in a probabilistic standpoint, and you look at maximizing a cost benefit ratio for a given level of protection. You can think about that in terms of a 100-year water level or a 500-year water level or a 50-year type events or for levels of protection or flood risk reductions for those. And so when we're evaluating the effectiveness or the changes that a potential structure would come into, one of the things that we look at is actually maximum storm surge for that area. And so the image you're seeing here up on the top left, this is the base conditions, the as is in the area of Houston and Galveston Bay. Over on the upper right, alternative D2, you can see, I don't know if you can see well, you probably can't see my cursor. There's a black line moving down the west side of the bay, and you can see the reduction that occurs. And that's where a proposed flood wall and levee system and navigation gates were added in. And on the bottom slide, you're looking at the solution differences of the project being in place versus the project not being there. And this is for a particular storm. The storm track can be seen in red on the lower left part of the slides. A little red line going through there, basically right over top of Freeport, Texas. It was a Category 2 storm, so a mild storm, a fairly slow forward speed, fairly sizable storm. And so you can see we have provided protection back behind the flood protection walls, but you can also see out in front of the flood protection area, there's actually been some increase in water levels. So this incidental flooding that comes with that has to be considered in the design. If you're lowering a particular area's flood risk, but you're raising someone else's, that has to be mitigated for as well. So on the next slide, what we're going to see here is the exact same storm, different. This is a. I'm sorry.
I'm sorry. Can we get a rewind to you?
Got to keep going. So this is a different flood protection measure that was being evaluated. This one actually puts the flood walls and barriers on the open coast out in front of Galveston and along Bolivar roads, and a large navigation gate over the inlet into Galveston Bay. So you can see the black lines over on the top right-hand side, and you can see the immediate reduction in flooding in the entire bay and in the Houston area on the bottom plots here. So a good bit of difference between these two different designs, and a good bit of change in the amount of flooding that was taking place. So this is the exact same storm that was run under both cases, and we're seeing these patterns. And you may think, oh, okay, clearly alternative A is a good choice. But when we move to the next slide, please. This is still alternative A. But this time we changed the storm track. We changed the storm conditions. Now this is a very rare event coming through. It's actually moving kind of west to the southwest. It's a Category 5, so a more intense storm and moving fairly slow forward speed. And you can actually see that in this case, we do have some reductions that occur in the storm surge, but there's also a good bit of back bay induced flooding, where the water is actually piling up from behind the flood protection structure. And so when we are looking at designing and considering the benefits and the consequences of building these structures, as well as the cost benefit ratios, we have to look at a variety of storm conditions on a variety of paths coming through to fully quantify the risk. We don't design to a particular event. We do go back and look at historical events, particularly when we're communicating with the public, because they have a memory of, oh, Hurricane Ike did this, or Hurricane Harvey did this. And so when we like to show how this project would have performed during that event, that's a powerful communication tool, particularly with the public, but not necessarily for design purposes. Next slide, please. Next slide. And so for doing this level of design, this level of analysis, we need very accurate models, numerical models that will predict the storm surge and waves. And we need those models to be dynamically coupled, linked together so that they're sharing information with each other during the course of the simulation and actually solving the problems in a coupled, combined way. And to do this, we're using a coupling framework. It's an emulator of the Earth System Modeling Framework, ESMF, and we're calling it the CStorm coupler with that. And that's the green circle there. And it allows information to be passed between models where appropriate during the course of the simulation. And so to do this kind of modeling, this kind of design, we break the physics up into the atmospheric components that come into the models, and they are pre-computed and high quality. Cyclone models is oftentimes what we're looking at here. We can also bring in extratropical models or bring in real-time forecast data from NOAA or the Navy or the Air Force or other European models, for example. Then we further divide the physics up in between deep water waves and near shore waves. The physics are slightly different. The dynamics are different. We use different numerical models for that as we go through, and the particular workflow is optimized by dividing these deep water waves and near shore waves up as well. I'm not going to get into that too much, but if you want to ask questions about that later, we can. And then in the nearshore environment here, this is where our circulation and surge model, ADCIRC, is communicating with S2 wave in this case, which is a nearshore wave model. We also have the ability to link in with a C2 shore model, which is a morphology change. That's still on a research basis on that, but it would allow us to model, for example, the barrier island breaching you're seeing in the lower left image on the screen right now. And so this is a workflow that's there. These models and these workflows are designed to help us provide this robust and standardized approach to model coupling. So the Army Corps uses this. This is also used, this type of models and type of modeling systems are also used by FEMA when they're evaluating the flood risk studies with that, as well as the Nuclear Regulatory Commission when they're looking at certifying nuclear power plants in a coastal zone. Next slide, please. And so a little bit about the coupling. It is very important that we have in these scenarios, in the nearshore environments, in particular in the overland environments, that we have dynamic linkage between models. And in particular, the circulation model needs to pass over water surface elevations and velocities to the nearshore wave model in order to get more accurate depth limited waves. So waves are depth limited. And so if we've got surge coming into an area, that means there's more water there, which means the waves can be larger. And then in turn, the waves alter the circulation patterns and the surge patterns through radiation wave stress gradients coming back over. So you're able to capture with this linkage here a dynamic where we're capturing wave setup. We're still, with these models, doing still water levels. We're not modeling individual wave trains per se. So there's still the wave overtopping component where you have the little individual waves lapping over something that needs to be done with a Bouziness type model coming in after you do this still water level piece of this. And so the coupling framework actually allows us to configure the models so that they communicate with each other and takes care of all the mappings that need to happen between structured meshes and unstructured meshes and structured grids with the unstructured meshes, and synchronizes them in time and space. So very user-friendly interfaces allow for that setup to happen. And then all the mathematical work of mappings and so forth take place by the coupler in a very fast and efficient way with that. Next slide, please. And so my area, my love is that center circle there and the numerical models with that. But they are, as I started off saying in our project designs, that needs to be cached in a probabilistic sense. We need to know a wide range of storm conditions that come into a particular area. And so we partner with statistics teams that come in and look at the storm climatology for a given area that we're modeling. And this can include both tropical events as well as extratropical events that are coming through. And as I said earlier, we do historical events from time to time, but most of these are actually synthetic tropical storms that are designed to represent the storm probabilities of a given area, from the very frequent storms to the very intense. So a 100-year storm, a 1-year storm, all the way out to a 10,000, 100,000 year type storm that may come through an area and design those. So on the front end, the statisticians are telling us these are the types of storms, and we work with meteorologists to develop storms to come into that. We run those through the numerical models to provide the response, the water response to those storm forcings, and then we hand those results back off to the statisticians, who then combine those in a joint probability method and come out with these annual exceedance probabilities and confidence interval curves across the areas for this. And right now, and I'll talk a little bit about this at the end of the talk, the next phase of this is actually integrating compound flooding events on the coastal side. So bringing in rainfall, bringing in runoff, and precipitation data into these as well. And so where you can have a storm surge combining with a very high riverine flow or a very heavy rainfall event, exacerbating the flooding even more. So that's an area that we're looking at actively of coming in for both the statistics approach for that, as well as the numerical approach to it. Next slide, please. And so I want to show just a few examples of some very large regional studies that we've done this high level complex modeling on. So the first one is the North Atlantic Coast Comprehensive Study. This was funded post Hurricane Sandy up on the North Atlantic coast of the United States, from Southern Virginia all the way to Maine. For that area, we ran over 1,000 synthetic storms. You can see their storm tracks down on the bottom left picture there. Along with those synthetic storms, we also ran 100 extratropical historical events to characterize the meteorology and the response for those. And for the hydrodynamic response, we looked at a surge only and a surge and wave only combinations, as well as combining those with a sea level rise scenario and a random tide assigned in with them as well. And the sea levels are initiated prior to the storm being run. This allows the models to capture all the nonlinear interactions that are occurring because of the increase in water level, whether this be with tides or be with a sea level range change. These models are typically the circulation models on the order of resolution down to tens of meters out to hundreds of kilometers in very deep water. The unstructured meshes allow us to put the resolution right where we need them. The ST wave is a structured grid model, nearshore wave model, and these are somewhere between 100 meter and 200 meter cell resolutions. And you can just kind of see those areas. So a lot of modeling was performed for those, this area. The next slide and the next study that we applied these to was the coastal Texas, so along the entire coastline of Texas. For that, we had 660 synthetic storms that we were simulating in this area, and we looked at 3 different water levels of present day, a 1 meter and a 1.5 meter, and a 0.5 meter sea level rise, corresponding roughly to the 35-year and 100-year on the intermediate curves going out. So we did this for the entire state of Texas, about 1,900 high-resolution storm surge simulations going on for those. Again, the same relative resolutions in the circulation and in the wave models for this area. Next slide. Most recently, we've completed the South Atlantic COAMPS study, or the South Atlantic study, funded after the recent hurricanes of Irma and Maria impacting the southern coast of the United States. And for this, we were modeling the entire South Atlantic coastline from Virginia all the way around the tip of Florida into the Gulf, all the way over to Mississippi, Louisiana state line. And then SAD, the South Atlantic Division of the Army Corps, they also have responsibility for Puerto Rico and U.S. Virgin Islands, which were also impacted by the same hurricanes. And so we modeled events there. In total, we had about 2,000 synthetic storms, and you can see the storm tracks covering these areas, and you can see some of the different parameters that are varied over each one of these tracks, dealing with the intensity of the storm, the size of the storm, and the translational speed of the storm, varying those to actually capture all possible combinations of types and designs of storms that are coming through. Next slide, please. This is just a look at some of the ADCIRC and ST wave names that were used. This one was for the Puerto Rico and U.S. Virgin Islands. To kind of give you an extent for those very large basin, the very large models, allow us to capture the basin scale effects and still have very high resolution around the project areas that we want to model. Next slide, please. Under the same study, this is actually a different mesh with a different focus on it. This was for the South Atlantic domain with the high resolution going from Virginia, North Carolina border all the way around the tip of Florida. About 12 million elements, unstructured elements there, and we have about 14 different ST wave domains ranging from 150 to 200 meter resolution up and down that part of the coast. Next slide will show you the model domains for the Gulf of Mexico, again for the South Atlantic. This one had about 15.6 million elements in it, and again about 12 or so ST wave domains relatively with that same resolution. So in all of these areas that you're seeing here, this is where the high resolution model results would come out from that. Next slide, please. This is just to show a little bit on the deep water wave model. In this case, we were using the WaveWatch 3 model, which was originally created by NOAA. It's a community-based model now, and a lot of groups are using this. The Navy, in particular, in the Army Corps, as well as NOAA and others. So we set up the WaveWatch 3 model to do our deep water waves, and then it provides boundary conditions to the nearshore waves. And we ran all of these storms that we talked about for the South Atlantic coast, in particular, on that across these basins in WaveWatch 3. Next slide, please. It gives a little bit of the calibration. This is specifically for the South Atlantic coast side of this, and very good agreement with data for several of the historical storms that we were running for validation and calibration purposes for the WaveWatch 3 model. Next slide. This is actually some of the surge and nearshore wave responses that we were looking at for Hurricane Maria coming out of this, and a decent scatter plot, QQ plot, comparing with high watermark data in Puerto Rico. With the high watermarks here, it was very hard to determine what was still water level and what contained, which ones contained wave runup, which these models weren't capturing. But even so, we were doing a very good job representing the maximum surges in the area. Next slide. This is for Hurricane Matthew. So this is the one that was used for the South Atlantic validation calibration. And again, we had a lot more high water marks for this and doing an overall very good job of model data predictions with no obvious bias one way or the other in the calibration. Next slide. Next slide. So when we do all of these hundreds and thousands of model simulations, we use the CStorm production system coming through for these and making use of the Department of Defense supercomputers, as well as some pay-for-use supercomputers now. And we have a production system that allows us to set up and simulate any one of these condition events, all the way from the setup of it, all the way through to the archiving of results. And so this makes it very easy to launch jobs and keep track of jobs coming in for these, as well as to store in an efficient way our data for reuse and archiving purposes, which I'll talk a little bit about in a few minutes. So with this production system, it really allows us to remove a lot of potential for human error trying to run these hundreds and thousands of simulations going through. Next slide. Actually talks really about the API, the hierarchical design of the naming conventions and the storage conventions for doing all of these models, synthetic tropicals, extratropicals, so forth, the different sea level rise scenarios you may be doing, whether you've got river forcings in them or not, different river forcings, whether you were including waves or not, different configurations. Were you using an existing conditions mesh, or were you looking at one that had the project included in it? So all of this is in part of the naming convention and the storage, and allows for very rapid and quick access to that data. Next slide. Then a large percentage, well, actually a very small percentage of the data, less than 1% of the total data that is produced by the numerical models, makes its way into the coastal hazard system, which is actually a nationwide database and portal for mining this data. And what we get are the statistics that are computed and time series results at save points. So typically on a study where we may have 1 million ADCIRC nodes, I'm sorry, like 3 million ADCIRC nodes, we may only have 20,000 save points that we're producing statistics data at and putting that out for public consumption. And so this is part of the coastal hazard system. It's publicly available. You can see the address down. I highly recommend you go to it if you're interested in looking at what's there and available. Basically, any place we've done one of these large studies, you can click on the area, click on a save point, and see your annual exceedance probabilities from a 1 year all the way out to roughly a 10,000 year event for both water levels and wave heights. Next slide is also about the coastal hazard system. This kind of gives you an idea of some of the output that you could look at in the upper right-hand corner. You can see what the curve would look like. And in this case, we're actually comparing that location's results to a study done in the FEMA, latest FEMA flood map studies. This is for an area in coastal Texas. Again, the address is there. So we have several different confidence limits that are given for the modeling to allow for different design use, different project use. And so this data is used by not only the Army Corps, it's also used by municipalities as well as AE firms and others in their design and working on projects that are available. Next slide, please. I know I'm running a little short on time, so on the rapid response, let's go ahead and move to the next slide. This is when our districts come to us and ask us to provide information about an impending storm. I don't like to use the word forecast because we're not really forecasting. We are providing a predictive mode of our models. Next slide, please. And so this is if it starts up, this is an animation of Hurricane Sandy, and this is from some examples that we gave to our New York district prior to Hurricane Sandy coming in. And you're looking at the inundation in the entire New York bight coming in, and then on the right hand, upper right hand, this is actually Lower Manhattan, and you're looking at the flood levels in time as they come through. And this is using a forecast meteorological product for the area that was developed there, as compared to some of these very high accuracy reconstruction wind fields that we oftentimes use. Next slide, please. Continuing along with that, this is an example we did of Hurricane Harvey, again using forecast winds from the National Hurricane Center and the sea storm modeling system here, and a very good response as it turned out. This is again for Advisory 20. These simulations, we were doing a 5-day forecast period, and we turned those around in less than 2.5 hours using about 1,700 processors on the supercomputers to give to the district so that they could use those for their planning purposes, seeing if they needed to sandbag some certain areas or reinforce some flood structures in the area. Next slide, please. I'm actually just going to skip this one. We did something similar for Hurricane Irma Lake Okeechobee. And then this is Hurricane Laura from last year. And in this case, the Galveston district was asking, well, we know what the best track is looking like and what are the surges looking like with that, but what if this thing shifted to the west and came over top of us? What might we get? And so the red track you're seeing here is the hypothetical what if, and the color contours are the maximum water surface elevations. And you can see in this case, we were bringing about 12 to 15 feet of water into the area if that advisory shifted the track. Next slide, please. Next. And as I alluded to a few times, so we're taking these very high resolution coastal models, and now we're taking our expertise that we have on our hydraulics inland flooding side, and we want to look at how do we integrate these two together so that the surge is impacting the river flows as a tailwater, and that the river flows are impacting the surge as well, and the so-called transition zones where these come together. And then looking at synthetic rainfall events to match up with these synthetic hurricanes, and looking at it from a statistical standpoint. What is the appropriate river flow to match up with a 100-year water? Are they both 100-year river flood and 100-year coastal storm surge, or is it something different? The data records that we have are very limited, and additional measurement data is really needed for those. And looking at creating rapid flood prediction hazards. So one of the reuses of this data that we're producing is actually through a machine learning, artificial intelligence type environment. We can actually create response surfaces out of all of these pre-computed storms and then use a very rapid, in a matter of seconds, forecast from those machine learning type algorithms to give a forecast scenario for that. Next slide, please. So this is just an example of some of the complications when we're considering tying in riverine flow with coastal surge. Sometimes we have a nice clean river boundary where you can plug them in at, and there's no problem there. But then other times, like in the lower right-hand corner here, this is the Houston area again. The surge model has to go so far inland that you're capturing very much all of the tidal creeks and channels in there. And the surge model can't really model those at the level of detail that they need to, or as accurately as a traditional hydrologic model could. But figuring out how to tie those in together when you don't have those clean boundaries is certainly something we're looking at. Next slide. And then looking, as I said earlier, about the probabilistic coastal hazards analysis in combination with parametric rainfall models and bringing those in as yet another parameter in the overall joint probability methods, which is going to do nothing but increase the number of events that are having to be simulated and looking for computational efficiencies to leverage. Next slide, please. So I truly appreciate your attention. I'm sorry I had to talk so fast to move through that. There was a lot of material to cover, and I want to make sure I leave plenty of time for Dr. Doyle to talk. Thank you very much.
Thank you very much, Dr. Massey. Our next presenter is Dr. James Doyle. Dr. Doyle holds a PhD in meteorology from Penn State University. He is the senior scientist at the U.S. Naval Research Laboratory in the Marine Meteorology Division in Monterey, California. Dr. Doyle leads a multidisciplinary program of scientific and applied research in marine meteorology and related atmospheric sciences focused on developing new numerical analysis and prediction systems to support Navy and DoD operations, and also to provide new understanding of the environment, including its impact on naval platforms, sensors, and systems. He leads the development team for the Navy's operational, I'm not sure how to say this acronym, I think it's COAMPS-TC, the tropical cyclone model, and is one of the lead scientists for the mesoscale.
Hi everyone, I'm Jim Doyle from the Naval Research Lab in Monterey, California. I'm here today to talk about tropical cyclone intensity and track prediction using the Navy's prediction system called COAMPS-TC. Thanks very much to the folks at the Air Force and for inviting us to present. Really appreciate that. I'd also like to acknowledge my co-authors shown here at NRL. This group of people work very hard on COAMPS-TC. I'd also like to recognize my colleagues at NRL Ocean Science Division at NRL Stennis, and recognize our sponsors at the Office of Naval Research. So the NRL Marine Meteorology Division is in Monterey, California, and conducts the DoD's only full spectrum from basic to applied research to operational transitions research program in the atmospheric sciences, and the only DoD program in numerical weather prediction. We work closely with our partners at the Navy Fleet Numerical Meteorology and Oceanography Center, or FNMOC, and this partnership is really unique, and we work close hand in hand with them as we transition models to operations, and they run the models operationally. So our goal is to better understand the environment and its mission impacts on, so that the Navy can better simulate it, predict it, and help the warfighter make better decisions. Why are we so interested in tropical cyclones? Well, first of all, a little bit about tropical cyclone impacts from a societal perspective. Property damage costs of tropical cyclones equal or exceed those of earthquakes and every other natural type of catastrophe. Global estimates of TC damage is 26 billion per year, with single storms ranging up to 150 billion. TC are obviously responsible for many casualties and deaths worldwide annually. Just as an example, Typhoon Nargis was a really strong tropical cyclone that caused a terrible natural disaster in Myanmar and caused catastrophic destruction and at least 138,000 fatalities. On the DoD side, of course, tropical cyclones could cause great impacts. We need to look no further than back into World War II with Typhoon Cobra, which caused catastrophic damage to destroyers, destroying aircraft and nearly 800 lives lost, showing the potential for tropical cyclones to have a negative impact, of course, on the Navy. We also have other examples, including Hurricane Andrew, which resulted in heavy damage in Homestead Air Force Base in Florida. Also another Air Force Base in Florida, Tyndall, was damaged heavily during Hurricane Michael recently in 2018 with over $1 billion in aircraft losses alone. So tropical cyclones are a threat to onshore DoD infrastructure and Navy ships at sea. Well, over the years, there certainly have been marked improvements in tropical cyclone forecasting, and these are two graphs that summarize those improvements. These are courtesy of National Hurricane Center and show the official forecasts for hurricane track on the left and intensity or peak winds on the right. First, if we look on the left, we could see marked improvements with time in terms of the forecast errors in terms of position or track. The 1, 2, 3, 4, 5 day forecasts are shown here. And one can see readily that there are really steady and dramatic improvements to track forecasts. For example, 5-day forecasts today are as good as 3-day forecasts today are as skillful as 5-day forecasts were a couple decades ago. That's really remarkable improvements, one of the great stories, success stories of science. On the right side is the intensity error as measured in terms of peak wind speed or knots. And you can see the story is similar. We're slowly driving down these errors, but much less rapidly. So the improvements in terms of intensity is happening on a slower time scale, and you can see there's a lot of variability from year to year. Some of the seasons are quite tough in terms of predictions, and it's reflected in higher intensity errors. A lot of these improvements are built or occur based on the backbone of numerical weather prediction. Of course, there's improvements in forecast techniques as well as observations and other aspects of the forecast process, but the weather models are a big part of what the improvements you can see here. And this is highlighted in a paper by Peter Bauer, which appeared in Nature. And he and his colleagues go on to say that advances in numerical prediction represent what's called a quiet revolution because they've resulted from steady accumulation of scientific knowledge and technological advances over many years. And a lot of these advances have been borne out in these reduced track errors. Intensity is much more challenging, and that's part what we'll focus on today. Though we are making progress, progress is not rapid, it's not easy. Very hard problem. So we have a COAMPS-TC system. This is the overview of the system. And the system is a specialized version of the Navy's mesoscale NWP model. It's designed to predict tropical cyclone track intensity and structure, what we call structure or wind radii. Has lots of specialized features, including physical processes. It's coupled to an ocean model, the Navy NRL Coastal Ocean Model, NCOM. We have moving nests that follow the storms, and these examples shown below that are, you can see, are simulated radar reflectivity for Hurricane Dorian as it moves up along the coast. You can see that the model with the high resolution mesh following the storm can resolve these individual rain bands and changes in the intensity of the storm. Here on the right is the SST coming from the two-way interactive NCOM model, and you can see bursts of cooling that occur as the hurricane mixes some of the ocean mixed layer below and cools the sea surface temperature. So these interactions with the ocean are extremely important. The model is operational at Fleet Numerical Meteorology and Oceanography Center We have two different deterministic versions. One is run from the Navy Global Model NavGem, and the second one is run from the Navy or from the NOAA model GFS. That's the global model. The Navy NavGem's version is denoted as COTC, and the version running off of the NOAA model is CTCX. We also have an ensemble that runs operationally at Finnmark, 11-member, 4-kilometer horizontal resolution, and this is based on the NOAA GFS. So let me take a little bit of time to explain the history of COAMPS-TC. Since this is an innovation series, I want to highlight some of the innovations and the way we got those into operations. This is a graph of the time. These are the years on the x-axis. On the y-axis is the technology readiness level, the TRL, going from basic research to applied research and into operations. So our job at NRL, of course, is to innovate. And this is really a story of innovation in the area of tropical cyclone intensity and structure prediction, where the U.S. Navy has become an international leader, both the science and forecasting of tropical cyclones. So what you'd like to see here is a plot of TRL versus time, and you'd like to see positive slopes. The more positive the slope or the steeper the slope, the more rapid the innovation to implementation process. Back in the earlier times that we started working on this 15 or 20 years ago, we were doing some basic science associated with processes and modeling at tactical scales. This included the Navy's tactical scale atmospheric model COAMPS, coupling COAMPS to the Navy tactical scale ocean model. That began in a 6-1 type of program, basic research. And we were able to invest in time using some help from NRL, capital investments, and ONR programs as well. And in about 10 years, we went from the idea of a concept of a tropical cyclone model that had high resolution that was coupled. So it went from an idea to a demonstration project, and that took about 10 years. In the world of numerical weather prediction, that's at a pretty good rate of innovation. Nothing to a new operational world-class model in 10 years. But that's really just the beginning of the story. That capability elucidated understanding, modeling shortcomings that were leveraged to launch new field campaigns, working with Office of Naval Research, national interagency efforts, working with NOAA and NASA to focus on TC intensity, which I referred to earlier, a super hard problem. And from 2010 to 2013, we went from real-time support of a field campaign to dedicated TC prediction and operations, providing guidance from our warfighters. So we went from this sort of prototype system now into operations by 2013, which was when we first fielded this. So this is even a better rate of innovations. You can see this slope is steeper. And our initial 6-1 pathfinding that took 10 years to mature yielded a second innovation cycle of only 3 years. But it just doesn't end there. Ever since 2013, we've had a 1-year innovation to implementation cycle where we're learning from our operational forecasts, leveraging that knowledge to identify new 6-1 and 6-2 ideas, getting those proposals funded, and getting the latest and greatest innovation into the model for the next season of the tropical cyclone model. So we've gone from nothing basically to one of the top TC intensity forecast models in the world through a series of multi-scale innovations to implementation cycles. In a sense, the linchpin in all of this was the timely availability of a large amount of computing that enabled us to do this real-time support of the initial TC field campaign. So in order to keep fueling this year-to-year improvement cycle, we not only need smart people, of course, working on the problem, but we also need adequate computing. And so more research computing and operational computing and associated resources are really necessary to be able to continue to work this problem. Right now, our models run on about 1,000 cores over the next 10 to 15 years on the same time scale about as you see on this plot. Our innovation will enable us to take advantage of, we think, of 1 million cores or more. So we're really tied closely to innovation in computing. A couple of highlights from the deterministic and ensemble system that we have for COAMPS. First of all, this deterministic model, as I mentioned, it's a very good model. It's a top model for intensity and track, performing very well in the West Pacific and West Atlantic. There's some recent internet headlines about COAMPS-TC being the top intensity model, one of the most reliable models. Competes very well with the NOAA models. We have this new ensemble system. It went into operations in 2020 at Finnmark. It was the first operational high-resolution TC ensemble systems anywhere that's available. And we've tested it with 21 members in the last year. I'll show you some examples. This was done in real time in 2020. Our partners at the DoD Joint Typhoon Warning Center has found COAMPS-TC ensemble to be very useful. And they highlighted here in one of the quotes about its impressive performance for one of the tropical cyclones in the southern hemisphere. Just quickly looking at the Atlantic Basin statistics, this is the track mean absolute error. Of course, lower values better against forecast lead time out to 5 days. And this is the mean absolute error on the y-axis in terms of position in nautical miles, lower being better, as I mentioned. So COAMPS-TC here, very competitive with the other models this past year in the Atlantic. Had lower track errors than the NOAA models, actually, so it did very well. On the intensity side, comparing with some of the intensity models at NOAA, CTCX, COAMPS-TC was very competitive. The NOAA HWRF model was a knot or so better, but overall, right in the mix. Very low bias as shown by this dashed line, which is the systematic error. So close to zero for these models. That shows you how good they've become. And then for looking at the notion of rapid intensification. So by rapid intensification, we mean storms that intensify by greater than or equal to 30 knots in 24 hours. You can see from these plots, these are intensity errors, the mean absolute error in solid for 3 different models, including CTCX in blue, and their bias in the dashed. You could see for the storms that had rapid intensification the first 24 hours, you can see very rapid growth with significant low bias. So it's under predicting this development. If we look at the cases where there was no observed rapid intensification, we see much slower air growth, minimal bias, and the predictions are beautiful. I mean, not relatively low errors. And so if we had storms that never underwent rapid intensification, our intensity statistics would be much better. It's these storms, these special storms that undergo this really fast increase in intensity is the toughest for the models and the forecasters. This just shows a plot in terms of evaluating rapid intensification of these models like COAMPS-TC. We can see some progress in this. So this is a plot of the success rate on the x-axis versus the probability of detection on the y. You'd like the model to be along this center line, and you'd like to be in the upper right corner. And you can see the difference between 2018 and 19. These dots are for different forecast lead times. COAMPS-TC has markedly improved in the last couple of years as part of this innovation cycle. And you can see for the first time, the ratio of the relative frequency of RI is about 1 between COAMPS-TC and what's observed. So it looks like we're on the right track. We obviously need to improve the skill quite a bit more. There's a lot of room for improvement, but making very good progress in the last couple of years. One of the reasons for this progress is we work closely with the Office of Naval Research on field programs. And here's 2 field campaigns that we worked with ONR on. One was the Tropical Cyclone Intensity Experiment, in which we had an aircraft, a high-flying WB-57 from NASA, flying over a storm called Patricia. That was one of the strongest storms on record. We dropped these, you'll see these little dots, and these are dots indicate locations where we deployed instrumented packages called drop wind sondes. And this is a new technology that we worked with folks at Yankee Environmental Systems with, and they have a new technique to be able to allow a lot of these dropsons in the air at once. And this, we actually dropped over 40 across this very intense center of the storm, which is a world record. Working now with ONR on an experiment focused on rapid intensification. We actually have some nice results last year for several hurricanes, which we observed periods of rapid intensification. We're hoping some of these ideas that bubble out of these field experiments can help improve this. Example from last year is Hurricane Laura. You can see here's the best track in black. This is a plot of intensity versus the date versus time. You can see the storm went through a rapid intensification cycle and then hit land and rapidly weakened. All these different blue lines are different COAMPS-TC forecasts. And you could see these, the model did a remarkable job at capturing the rapid intensification of Laura and did a remarkable job with the track of Laura. And this little inset here on the right shows where all the dots are the landfall locations. So the model was very consistent for a lot of different initialization or forecast lead times where the storm was going to hit. So it's a big success story. But I don't want you to believe that all of our forecasts look that great. And this is one from Epsilon last year that was out over the water and went through a rapid intensification cycle, as you can see by this black line. So it intensified, and all these blue lines show the COAMPS-TC forecast. The model was not able to forecast that intensification or even maintain that rate of intensification. It was a big miss by the model and allows us to go back and revisit this and try to understand better what was missing in the forecast model. Mentioned earlier, the model is coupled to a ocean model developed by NRL Stennis called NCOM. The air layer that exists above the sea surface we call the boundary layer or marine atmospheric boundary layer, and that layer is tightly linked to the upper part of the ocean or the ocean mix layer, and it exchanges information through air-sea fluxes. So as I mentioned, the standard version of COAMPS-TC is coupled to this NCOM ocean model. And we're experimenting with air-ocean wave coupling, and this is being spearheaded at NRL in collaboration with NRL Stennis. It's by Sue Chen. This is an example on the right of Hurricane Florence, and we're working closely with a number of different oceanographers, including Beth Sanabia at the U.S. Naval Academy. And they've been, the last number of years, been dropping instruments in front of storms to understand better about the ocean response and how that influences the storm. And you can see a series of profiles on the left. You can see the market cooling underneath Florence that occurred, where the temperature dropped by 3 or so degrees Celsius as a result of the mixing from Florence of the upper ocean that cooled the sea surface temperature. And that has a big impact on the fluxes, which impacts the intensity of the storm. Speaking of Florence, we also produce rainfall forecasts, and this is just an example from Florence that shows more than 25 inches of precipitation predicted 5 days in advance. And the verifying precipitation analysis shown in color on the right, and you can see more than 30 inches was observed in some locations. So very good forecast. The track was predicted very well in this case, and the model was able to capture this precipitation structure quite well. We have some new innovations related to surge modeling, and we're supporting several different surge projects, including a new National Ocean Partnership Program project and several Navy projects related to creating tropical cyclone reanalyses that have been designed to provide very accurate meteorological forecasting to support the storm surge and inundation modeling. And so this way that they have very accurate tropical cyclone forecasts and simulations to be able to drive their models and learn more about their modeling systems and shortcomings. So what you see here are plots of track, wind speed, and sea level pressure for Sandy, Matthew, Irene, and Florence shown here. And the red lines are the model reanalysis. The black is the forecast. The black is the best track, or the so-called observation. You can see they're all really close. You can hardly see the red line in a lot of cases because the red line agrees so well with the observations. We really constrain the forecast based on the best track. So we've done about 10 different storms for using this technique, and it's, I think, very valuable in terms of learning more about the effects of the meteorological forcing on storm surge. We also verify in the lower right with buoys, as shown here. I'm going to say a little bit about ensemble forecast. So we're building on the ideas of Edward Lorenz, who's the father of chaos theory, who wrote "One flap of a seagull's wing may forever change the future course of the weather." Of course, this is chaos theory, and this shows the chaos attractor shown here. He received the Kyoto Prize in 1991 for profoundly influencing a wide range of basic sciences and brought about one of the most dramatic changes in mankind's view of nature since Sir Isaac Newton. And so this is really the basis for ensemble forecasts. I mean, conventionally we do deterministic forecasts. We start out at the initial time with a single forecast. There's no flow-dependent estimate of forecast uncertainty. We have no way of estimating the uncertainty. But if we make many forecasts with slightly different initial states or model formulations, taking advantage of these concepts of chaos theory of Lorenz, we find that the spread among these forecasts can give us information about the forecast uncertainty and give us a probabilistic basis for the forecast. This is just an example of some of the products from the COAMPS-TC ensemble system for Hurricane Laura that I showed you earlier. First of all, on the left, it's the track colored by intensity, the upper left. And then we have different probabilistic information graphics, one for the intensity forecast in the upper middle, with the magenta showing the probability of Laura developing into a Cat 4 or 5 storm, this case being more than 40%. Also, probabilistic intensity change forecast, so probability of exceeding the threshold of rapid intensification shown in the magenta, which is greater than 50%. So these are very valuable for the forecasters to give them lead information on what storms and what storms may intensify and when that may happen. We also have graphics for the intensity and the winds as well. Just to highlight one of the storms, this is from this past year, Cyclone Amphan, and it was in the northern Bay of Bengal and had caused significant damage in the northern Indian Ocean, $13.7 billion, 128 fatalities. And you can see these lines show the forecast from the COAMPS-TC and 21-member ensemble that we were running in real time. This is from the nice work of Will Kamarame. These are colored, so these color lines are colored by the intensity. You could see all of them were Cat 5 up to a point just prior to landfall, and you could see varying degrees of de-intensification as the storm made landfall. Nevertheless, the model gives very nice probabilistic guidance to the intensity and location of the landfall of the storm. Just to mention that we do a lot of different verification methodology for the ensemble forecast. One of them is we just compare the ensemble control forecast, which is a deterministic, versus the ensemble mean. So we take all those members and average them. So this is a very simplistic way to look at the value of the ensemble, and the ensemble mean looks as good or better than the control at all lead times for the track. And intensity, this green line actually shows the ensemble mean is 1 to 3 knots better than the control. Obviously, additionally, with the ensemble, we get a lot of probabilistic information that can tell us about the spread and uncertainty. Just a note about the resolution, we've been doing experiments for future transitions to operations with increased horizontal resolution, and we've looked at this storm I mentioned earlier, Patricia. And this just shows the failure of the operational models at that time in 2015 to capture this terrific intensification rate that Patricia showed, going from about 50 knots to the observed 185 knots in about 36 hours. This observed 185 knots is the strongest storm on record for the Western Hemisphere at the time. Models barely got above 110 knots. You can see as we increase from 5-kilometer resolution to 1.7-kilometer resolution, we do a bit better, and then down to less than a kilometer resolution, the model does actually quite well at capturing the peak intensity and that intensification rate. So high resolution is necessary, but not sufficient to be able to capture this sort of intensification. We need also complementary efforts related to the physics, so the planetary boundary layer, the coupling, the microphysics, also something we call data assimilation, of how we bring in the observations and start the model off. We're also working on new physics related to sea spray, so the waves breaking in tropical cyclones and moistening the lower part of the atmosphere, we think could be an important component, and this improves some of our rapid intensification accuracy and cumulus parameterization as well. So this is representation of the thunderstorms. And this gives us some advantages related to the forecasts of the wind radii. And so there looks to be some promise on that end. Also, we're exploring some new methods to be able to take in satellite data and use that data to start the model off. So we're using something called an ensemble Kalman filter. So it's an ensemble methodology using very frequent ingests of the satellite observations to estimate the new state of the atmosphere when we begin the model. And this is just demonstrated in this figure on the right. This is once again for Patricia. So we have this very tight inner core when we use this data assimilation method that we call all sky radiance assimilation. So typically a lot of the satellite data isn't used where we have clouds and precipitation. It's very hard to do because it can be contaminated by those the clouds and precipitation. But using this methodology, we're able to use a lot of this data in these regions of clouds and precipitation. We can analyze a much tighter core to Patricia, similar to the satellite observations shown at the top. Comparing without satellite data, it's a much more disorganized storm. So it looks really promising. We're very excited about the capabilities. Looking at the future, we have a system called Neptune that we're developing, this next generation global regional system. And it will be first transitioned as a global system, as shown here on the right. It's a very flexible system. It uses spectral element numerics that allow us to run on modern computational architectures and be able to take advantage of very big computational systems. It has the capability of also running in a limited area mode, as shown in the upper middle. And for the future, we're considering the possibility of adaptive mesh refinement. This allows one to utilize resolution where you need it. So you could see the grid cells refining where the tropical cyclone is. And this is demonstrated in a shallow water model, but it's something that we want to consider for future development in the 5 to 10 year period. Just a note about Tropical Storm Fred. It's a relatively weak system. It's still forecasted to be weak. You can see the CTCX deterministic takes it off the west coast of Florida. The TC ensemble keeps it relatively weak, keeping the storm at, say, 50 knots or less. There's a few members that do develop it, a relatively low probability, but not out of the question. So let me summarize. COAMPS-TC provides the Navy and DoD with world-class TC intensity track and wind forecasts. We've made market progress through systematic and steady evidence-based science and innovation in tropical cyclone models and observations. COAMPS-TC is the, really one of the top flyers, top shelf models for intensity and track that we have. It provides some really skillful forecasts of intensity, track, and structure. There's a web page here that contains the COAMPS-TC forecasts that are available in real time. NRL also provides tropical cyclone discussions on an ad hoc basis on Microsoft Teams flank speed for storms that threaten the US, and this was very popular last year. Some of the gaps, the next frontier is really this rapid intensification problem. There's lots of aspects that are really challenging, and we're working hard on that. We need to improve the representation of coupled processes. This includes the ocean, land, storm surge, also coupled observations and data assimilation. New data assimilation methods in tropical cyclones are needed. And I mentioned the all-sky radiance assimilation is really promising. Increasing emphasis on high-resolution ensembles are needed. Mentioned the COAMPS-TC ensemble that's in operations. It's really a great new innovation. There's opportunities for new collaborations within DoD and the civilian sector, including our colleagues, Dr. Massey at the Army, and our colleagues in the Air Force as well, and our colleagues in the civilian sector. Thanks very much for your attention. My contact information is here below. I really appreciate you listening to this presentation, and welcome further contact if you want. Drop me an email. Happy to respond. Thanks very much again.
Dr. Massey, are you still on the line?
Yes, I am, Callie.
Okay. So we had one come in for you. It was, given the National Weather Service has predictive responsibilities for coastal storm surge over CONUS, does and can CHL provide such capability OCONUS where we have DoD forces stationed?
Yes, we can. And we are asked to do that from time to time, and we do that. As you were seeing from Dr. Doyle's, they are operating their models around the world as well. So there's multiple capabilities across the DoD for that. The particular pre-computed for OCONUS military facilities and areas that would want more study, we can do the same kinds of large regional scale studies we've done in the United States, elsewhere as well. So we wanted to really characterize and look at facilities overseas, our military installations, for example. We can do that, quantify that. In fact, as we've worked with some of the sites overseas already in doing just that exact same thing, without trying to give away too many details. Sorry.
All right. You mentioned early in your presentation that models and structures are built on precedents with that kind of risk calculated into them. With the increased number of storms each year, do you find that the models are still accurately capturing the risk that the structures are built to?
Yeah, I mean, that's a great question. And as I was saying earlier, like when we design all these synthetic storms, for a given area, that really encompasses all the types of storms that come in for the area. And then we are looking at, historical data to give us a recurrence interval for those storms to know, how frequently this particular storm is or this intensity is. And so what would happen is as the historical record lengthens, as we start to see potential changes in the storm climatology, really about intensity or the recurrence of those, then the statistical weighting on the results can be updated. Then you can go in and look to see, hey, yeah, under a sea level rise or under this new climate scenario, what used to be a 50-year event is now a 35-year event, for example. So we are seeing sometimes evidence of those things happening. And in those cases, what was built to a 50-year, water level, 20 years ago, in another 10 years, it might not still provide a 20-year level of protection or a 50-year level of protection because of the change in climatology with that. Those kinds of things are factored into construction. We do consider sea level rise scenarios. We actually are required to do that for every project that we're looking at. Currently, there is really no guidance on any kind of change in the storminess of an area, the recurrence intervals of a particular storm itself. more intense but less frequent, or vice versa. So we're really looking for science to help us categorize that, and then from that we can put that into policy guidance.
Okay, and on a similar thread, I guess, are you noticing that with the heavier rains coming, with a lot of these storms, that it's changing how sedimentation aggregates in certain areas? And is it changing the flood level rises and the way the water moves in different cities?
Yeah, absolutely. I mean, with record floods coming in, you get movement of sediment that hasn't maybe occurred in 100 years or 500 years like it has before, because of the level of water coming in. And then, of course, with land use types changing and development and everything. And looking at those, particularly in a coastal compounding event, we are seeing an increase and a change in how not only the water levels themselves are moving and propagating in, but the sediments coming down the river in those. So that's still an area of active research, in particular trying to combine these coastal and riverine systems, including the riverine flows and the water quality and the sediment that's in those as well. But that's something that municipalities are very interested in. The Army Corps is interested in that from a dredging perspective, as well as a safety component as well.
Okay, I just want to check real quick. Has Dr. Doyle joined us again? Okay, I think we may still be having some technical difficulties with him. We did get another question though. If a new model comes out that you want to use, how do you standardize the inputs and outputs of that model to fit in with the others in your system? And is it difficult?
Right. So I think that, that's a great question. And so the Corps of Engineers and the CHL in particular, for the models that we use, our HH&C COP preferred tools, we are standardizing the input and output to those models. We're actively doing that to make it uniform across all the models that we have as well. And so right now we rely heavily on well documentation for any one model if you want to bring another one in so that it fits into a system. But the coupled system itself, this is done through computer memory. It's not done through file IO. And so with these very high level production codes with that. And so because you're doing code structure changes and you're doing numerical programming in there, it can take anywhere from a few months to a year to a year and a half to integrate a new model into a tightly coupled system that's really optimized for production level use on the HPCs, using something like the Earth System Modeling Framework, for example. Softer coupling, where you are doing it with files, that's certainly a first avenue into it. Does this work? Proof of concept piece of that. And again, it gets around sufficient documentation for the models you're using now. And as we move forward in the next year or two, where we're homogenizing the file types and the metadata and the data structures across the board, then that will become even easier and less time consuming, looking at weeks to months instead of years, for example.
Thank you. Okay, do we have any more questions for Dr. Massey? Okay, yes, one more. So you may have already answered, but are the model results for the Army DoD locations used to update the Army Climate Assessment Tool?
I will have to look at that. I have heard of the Army Climate Assessment Tool, but I'm not familiar enough with it to specifically answer that question. So I'm going to make a note of that. And Ms. Tucker, if you'll get in touch with me, hopefully Ty Daniels can give you my email, and I'll get back to you on that specific question. Sorry, I couldn't answer that today.
And Ty, would you mind putting your email in the chat here so that people can reach out to you for follow-up?
Sure thing.
All right. So I had one more question. We have In the news right now, Hurricane Fred headed towards Florida, I believe. Is your organization tracking anything on Hurricane Fred right now?
We are not actively modeling that. As I said, oftentimes when it comes to rapid response, we only do that when our districts ask us to do that. If they have a particular concern for that. Most of the time, the districts are looking at the National Hurricane Center forecast data, just like the rest, just like the people in the public are doing that. It's when they have a particular operational concern, then that's usually when they reach out to us and ask us to do something with that. Again, because our primary mission is not forecasting. We don't.
Mr. Lai, if you wanted to come off mute, you can ask your question.
Sure. No, I appreciate it. Thanks. So has it been problematic? So I noticed at the beginning of your presentation, there's an awful lot of compute required to run your models and to run your prediction applications. Was it a problem to garner the number of systems that you would need for that much compute? And have you looked into potentially using the scalable sort of monetized AWS cloud services for that compute on demand sort of responsiveness?
That's a great question. As you know, the DoD, I don't know if you know or not, but the DoD operates 5 different DSRCs, supercomputing centers across the country that we can use for research and operational needs. State of Mississippi has 2 of them, for example, one down at Stennis and one at Vicksburg at ERDC. Air Force has theirs, Army has theirs, Navy also has them. So these are very large systems, and they're used for a variety of research, not just this kind of modeling. And so in years past, we were always able to get the computational resources we needed and when we need them to do these studies. Typically, if it's a forecasting scenario, like, hey, we got to get this done, this rapid response, we've always been able to get the resources we need immediately or within a few hours by contacting the DSRC and getting them to block something off for a rapid, response kind of need for that. The large scale studies like the North Atlantic COMP, South Atlantic, and so forth, yes, these are using hundreds of millions of CPU hours and, obviously spanning several months. Up until the South Atlantic study, we had always been able to get all the resources we needed through the DoD HPC systems. When we came to the South Atlantic, that was such an enormous task. It was almost 300 million CPU hours in less than a year. So we did run into some difficulty with that, and that's where we actually purchased one of the old supercomputers and used that to finish off production runs with that. To answer your question about cloud-based services, yes, we are working with Microsoft Azure right now. I just we signed a CRADA with them and working with their AI for Earth. And we have actually at this point demoed the CStorm models, the coupled models operating very efficiently in the Azure cloud under an HPC type environment, similar to what we would have in the DSRCs themselves. And we're working with actually the HPC-MP program on that CRADA to look specifically at that. As part of that CRADA, Microsoft has actually awarded us a significant number of CPU hours in order for us to actually complete the North Atlantic study with a new sea level rise, one that we didn't use before. So we'll be using several hundreds of thousands, millions of hours, tens of millions, hundreds of millions of hours on the Azure to really put that through the test, see how efficient it is. And the beautiful part about that as well is we've got the data now on a cloud environment that will actually be publicly available, all of the data, not just some of the data like what we have on the coastal hazards now. So we're talking petabytes of data instead of just hundreds of gigabytes or terabytes with that. And the hope for that is other data scientists will be able to use that data to extend research and methods and just all kinds of possibilities moving forward. So really excited about some of that work that we're doing as well with Microsoft. And I have personal communications with other colleagues that are doing similar tests, not to those scales, but similar tests with Amazon as well. These are big physics-based models that are use MPI, message passing interfacing, parallel computing. The couplers themselves use that. And so, a typical web farm is not going to work. You really have to have a supercomputer type design, even in the cloud, to make that happen. Great question, and thank you very much for that, Vince.
You're welcome. Thanks for the answer. And I just a follow-on question. Have you likewise been working with Defense Innovation Unit on some of their AI projects and computer modeling?
I have not, but I would be very much interested to learn more about that.
So I retired last year from 20 years in the Army, and they were working on predictive modeling for firestorms, for flooding and fire control. Because there even in the commercial sector, there aren't those don't exist, right? So to deal with it, they really have been leaning on DIU. So I would recommend contacting them. That there's something would be interested to talk to you.
Excellent. Thank you very much. I'll do that.
And actually, we have reached out to them to present at an upcoming Innovation Connect, so we're hoping to get them on the schedule again. They have presented in the past too, so we do have a recording of them on YouTube if you're interested.
Excellent. Thank you.
Okay, another question just came in. In general, what are your thoughts on real-time storm surge products available today at NHC and their evolution?
It's good. So I can say the National Hurricane Center has definitely, a lot of improvements coming along. They're pushing as hard as they can to improve their forecasting. Not only the forecast, but how that's communicated to the public. They put a lot of research dollars and effort into surge risk in particular to the public from their products. They have a different mission, and really it's about loss of life and safety and evacuation and so forth. And so, they don't want to ever be low when they're wrong, so they would rather be a little bit high, and move people out of the way, and not have that catastrophe. So the accuracies and their approach to how they do that modeling is slightly different. So they use a lower fidelity numerical models oftentimes to do this, but they're using those lower fidelity models with a larger ensemble of storm possibilities and bringing in past known error estimators with this. So this is part of their probabilistic forecasting that they're using. So they get a very good response coming out of that. As Dr. Doyle was talking about, the ability to predict the track and the intensity of those storms is still an evolving science and a target. The track has become really good. They've made tremendous improvements on that. The intensities are still, a lot of work still needing to be done there. And of course, as a track shifts just a little bit or slows down suddenly or grows or whatever, then that can really alter the surge patterns for those things. And so taking an ensemble, taking a probabilistic approach to these and putting uncertainties around it is very important. And NOAA and the National Hurricane Center are doing a wonderful job with those. And like the models we were showing are much more deterministic, much higher fidelity model with less error for a known input, right? But when that known input, that storm track and that storm intensity can change so much, you've got to quantify those risks in that uncertainty arena by doing ensemble, and you can't do that. I
think this one was for Dr. Massey. It was, does the Coast Guard use this capability also? And I'm not quite sure what capability he was referring to there. So looks like Chip,
I know we've interacted somewhat with the Coast Guard from time to time for different things. Not really sure they're using it for, particularly for forecasting or anything like that, but for analyzing, the storm climate and the water levels and wave heights for given areas. That's certainly available to a wide range of coastal hazard system. And so I know we've interacted with the Coast Guard and those regards some, as well as the Air Force. We actively were helping with some of the Tyndall rebuild designs, and we were using these systems for that. So I'm not directly aware of it particularly being used, but I know we've interacted with the Coast Guard.
We do have a question, and it is the ability to discern rapid intensification improving since Titley's paper? Michael, last year seems to be an anecdotal case where the intensification was not caught.
Yeah, I think the community is making progress on rapid intensification. The models are getting better, but there's still many missing facets or interesting facets that the models aren't capturing. I mean, part of it is resolution. The models may not be at sufficient resolution, but there's also challenges related to the physical processes. And by physical processes, we mean the atmospheric convection. We also mean the air-sea interaction that happens underneath the storm. There are processes in the layer next to the ocean surface that we call the boundary layer that are really challenging, and models have a really hard time capturing those exchange processes with the ocean, but also the transfer of the heat and moisture and momentum from the ocean back through the atmosphere into the thunderstorms and convection aloft. So I agree, there's a lot of work to be done on that front.
Okay, one thing I noticed was the COAMPS-TC ensemble models are tracking the storm. You mentioned the damages done to DoD facilities. When you're doing your modeling, do you look at potential readiness to respond to storm surge at DoD facilities, or move assets and personnel out of the way of intense storms?
We're not responsible for forecasting, but our models are used by the Joint Typhoon Warning Center, who are responsible for taking the model forecast from not only COAMPS-TC, but other models. And they also have statistical aids that they use as well. And they're able to provide forecasts of the storms to the warfighter. So they disseminate those forecasts, and they do a really terrific job. And part of what they do, they have a system that was developed by NRL called the Automated Tropical Cyclone Forecast System, the ATCF. And that's a system that brings in a lot of these model forecasts and allows the warfighter to view them in a very nice way so that they can make forecasts and make decisions. And so these are then disseminated to the warfighter, to the Navy, to be able to make decisions based on those forecasts.
All right, did we have any other questions for Dr. Doyle in the chat? None seen. So thank you very much today for your time today, Dr. Doyle. We really appreciate it. Again, we'll get some good information up. Oh, some compliments to you guys as a Floridian. These were both great presentations. I have to agree with that comment. Used to live in Charleston and definitely watched some hurricanes come in. So this is always a fascinating topic. I did want to say both of our presenters today have presented, not the actual speakers themselves, but the organizations, the Army ERDC and the Naval Research Lab have both presented on Innovation Connect before. They also both have fantastic social media sites and other speaking engagements that are working in their own organizations. So that's going to conclude our Innovation Connect today. Thank you to both of our speakers for being here today. Our next one is scheduled for 9 September. Next month's presentations are going to highlight the need to operationalize AI throughout the enterprise, and we'll have the Joint Special Operations Command here to speak about that. Thank you all for taking the time to attend today. We appreciate your patronage here. This is a monthly event that we have, and it's been over a year now. So we love doing these. We get to learn a lot of interesting stuff here. And it's not without everybody's help that attends these. So if you are interested in presenting, or if you have a topic that you think we should reach out to somebody on, we'd love to hear from you. Video of today's event and other Innovation Connect events are going to be published on the Department of the Air Force Chief Data Office YouTube page. For more information on any of our future events or how to register, you can follow any of our social media sites, which are listed on the screen right now. And if you have any questions at all, you can reach out to Ms. Ty Daniel. Her email is in the chat, and she'll review your proposal and bring it to the team. We look